Good afternoon. Am I audible? Hello.
Yes, ma'am. Audible.
Okay. So this is week 4 fabrication techniques for MEMS-based sensor clinic perspective. So this is a problem-solving session. I'm Arpita Biswas, a PhD scholar in electrical engineering department from IIT Jodhpur. So this is about me. So this session we are going to solve some MCQ question, and if you have any doubts, so you can unmute yourself and you can discuss with me. So this is question number 1. What is the sentence? What is the sequence of step involved in CVD process? The first is the transport of gas species to the surface of the substrate. The second option is the reaction of the gas precursor at the surface. And third option is the deposition of oxide on the substrate. And the fourth option is absorption of the gas precursor into the subsurface. And the option E is removal of unwanted product and excess reactants. So please go through the options and please try to give the right answer. Take your time, there is no hurry, but at least try.
First option, ma'am.
Can you please little bit explain? Can you please explain why first option is the right answer? Little bit. if you have any knowledge.
The first one should be the transport of gas, ma'am,
Okay,
to the
then
surface of the substrate. Then second should be the absorption, and then the reaction will be happening. I'm thinking whether it is correct or wrong, like that. And the next one is the deposition of the oxide of the substrate, and last one is the removal of unwanted material.
yes, the right option is option A. You're correct.
Thank you.
Mhm. So next move toward the question number two. Which of the CVD process generate more hazardous toxic gases? First one is APCVD, second one is LPCVD, and third one is MOCVD, and the fourth one is PECVD. So which one is the right answer?
Fourth one, ma'am. Is it fourth one? Plasma
Can you
enhanced,
can you
plasma
please little
enhanced
bit
chemical
explain about
deposition.
the different type of CVD process? Then you can easily get the answer. What happened in plasma enhanced CVD system? Why it is used?
Actually, this is a deposition method, ma'am. Physical evaporation, physical enhanced, sorry, plasma
Sorry,
enhanced chemical vapor
plasma enhanced
deposition.
chemical vapor deposition. Yes.
Yeah.
So what? Why we
Actually, the
use
physical
plasma
vapor
enhanced?
deposition, two types of deposition methods are there. Chemical vapor deposition. The other one is physical vapor deposition.
Hmm.
And plasma means we are sending the gas, no, ma'am. So that's why
Okay.
this is
In
more
plasma,
dangerous.
it is forcefully in low temperature. We
Uh,
use this plasma enhanced chemical vapor deposition. Okay. But the
okay.
hazardous toxic gases are produces in mainly it is more hazardous toxic gases. It is in MOCVD.
MOCV.
Yes, it is MOCVD. Okay.
Okay, ma'am.
So next question number three. The advantage of chemical vapor deposition over the physical vapor deposition is first option is better step coverage. The second option is no corrosive gases. Third option is lower temperature process. And the fourth option is none of the above. What is the right answer? First, tell me which one is the physical vapor deposition. There are different type of techniques are present. Can you please little bit explain?
To be frank, I'm telling actually the last week one day I have joined 3 days back. So
Okay. So
three assignment I didn't do. Only fourth and fourth one day I completed. So
okay,
the
okay,
first
no
three
issue.
sessions I didn't watch. It's
Okay, no
pending.
issue. Actually,
Uh,
there are three different type of physical vapor deposition technique are present,
yeah.
like the thermal evaporation system, sputtering, and the
Uh,
E-beam
E-beam.
evaporation system.
E-beam
Okay,
operation.
E-beam
Yeah.
evaporation system.
Uh, uh,
And in CVD also there are different type of CVD process. And you have gone through the last question. Then
yeah.
atmospheric pressure, low
Yeah. Yeah.
pressure, then plasma enhanced, and one
Mm.
more I think.
Uh,
Yeah, the
low
MOCVD.
pressure.
Okay. Yes.
MOCVD. Yeah.
So now
Mm.
coming to the question, the advantage of chemical vapor deposition over the physical vapor deposition. So
Uh,
the
mm.
advantage of the chemical vapor deposition is the better step coverage. Okay,
Mm. Mm. Okay, ma'am.
because it is not the low, it is required the high temperature. In chemical vapor deposition, we record like atmospheric pressure also the greater than 1000 degree centigrade temperature we can use. And it is
Okay.
also no corrosive gases. Of course, in chemical vapor deposition, there are corrosive gases also produces also we are using as a precursor. Okay, so the right option is the first option,
Better,
better
better
step
strip
coverage.
coverage. Yeah. Mm.
So next question is question number four. A silicon wafer is doped by diffusion of boron to depth of 200 nanometer to define the active device area. Next process requires the deposition of a dioxide layer as an insulating layer, which deposition technique can be used so that the deposition profile will remain unaltered. So first option is APCVD, second is LPCVD, third is PCVD, and the fourth option is MOCVD. So which deposition technique can be used so that the deposition profile will remain unaltered?
Is it APCVD, ma'am?
It is PCVD. Okay, in PCVD, it does not alter the deposition profile. Okay,
Okay, ma'am.
so right option is the option C.
Okay.
So next move toward the question number 5. Dash is a chemical vapor deposition process. So first is the E-beam evaporation, second is the electrodeposition, and third option is the CVI, chemical vapor infiltration, and the fourth option is sputtering.
Sputtering, ma'am.
Dash is a chemical vapor deposition technique. Take your time, go through the question, then try to get the answer. Do you have any idea about the sputtering process? How it is like take place?
Sputtering.
Like
It is
here,
used for deposition, thin film deposition, ma'am.
yes, it is a thin film deposition process. But what happen inside? What is the basic principle? Like here is the
Sputtering.
target is present, okay,
Yeah.
and here is the substrate is present. So
Uh,
there is an argon bombard on the target.
yeah,
Okay.
the ions are getting
Yes, and
moved
it is like deposited on the
on
sample,
the surface of the substrate.
the surface of the substrate. Yes.
Substrate, yeah.
So now tell me, it is chemical vapor deposition or it is physical vapor deposition? Chemical vapor
Chemical
deposition
vapor
is means
deposition.
there is a
Chemical vapor deposition.
if if it is a chemical vapor deposition, what is like at first go through the like it is a chemical vapor deposition.
The,
What do you understand from this sentence? Chemical vapor deposition.
the
Like
chemical
here is some
reactions will be
chemical
happening.
reaction is there, na? But here
Yeah,
is
yeah.
not the
Using that
no, there is no chemical reaction like argon
oh,
bombard, and some of
yeah,
the
yeah.
part is deposited here.
E-beam evaporation, ma'am. Electron
No,
beam
in
evaporation.
E-beam evaporation also there is a E-beam also they have used on the target, and
Okay,
some
okay.
of the material is deposited on the surface of
Uh,
the substrate. So it is
okay.
also physical vapor deposition technique, sputtering E-beam evaporation. And
Okay.
second is electrode
Electron
deposition.
deposition.
No, it is also not. So
Okay.
chemical vapor infiltration is the chemical vapor
Infiltration.
deposition method. Okay.
Okay. Okay, ma'am.
So next move toward the question number 6. Which of the following statement is true for APCVD? First is the low sticking coefficient of the deposited material gives better step coverage. Second option is only the chemical reaction occur at the surface. And the third option is the deposition of precursor occur in the gas phase deposition. This reaches the wafer surface. And the fourth option is the none of the above. So please carefully go through the options.
So APCVD is decomposition of precursors occurs in the gas surface.
Which option is the right answer?
C.
Deposition of precursor occur
In the gas
in
phase
the
before
gas
this
phase
reaches the
before
waves.
the reaches with the surface. Is it true?
Decomposition precursors of this.
Deposition of precursor occur in the gas phase before it reaches to the wafer surface. When it is reached to the wafer surface, then absorption happen and then react with the material, and after that the deposition is take place. Okay.
Yeah.
So which one is the right answer?
None of the above.
No, not none of the above. One by one, go through the option.
Uh, Low sticking coefficient. Only chemical reactions occur at the surface. Huh?
And
I
what
think
about the
all
option
the
A?
no,
No,
it is.
this
I
one is
think
not the
B.
right. See, this one is
B.
not the correct answer. Okay. So
Yeah,
none of the
only
above also not. So
and
say
then
go to the
B.
second. Only chemical reaction
Chemical
occur
reaction
at
occur at the
the
surface.
surface. No, it is also not.
Then A.
So the first option is the right answer. Like
Okay.
C. Low sticking coefficient of deposition material give the
Gives
better
better
step
stick.
coverage. Yes, this option is the right answer.
Low sticking coefficient.
So next move toward the question number 7. Micromachining is the technique to technique of producing or fabricating MEMS device at a micrometer scale. The below diagram shows a cross-sectional view of the VOC sensor fabricated. Which type of micromachining is it is? First one is the bulk micromachining. Second is the surface micromachining. Third option is the both A and B, and the fourth option is the none of the above. And
Both A
also,
and B.
can you
A and
please
B.
explain why
Because
both A and B?
the VOC, it's combination of both bulk and surface, ma'am. That VOC is the full structure is it occupies
Why,
both.
where the bulk micromachining is used and where the surface micromachining is used? Can you be little bit explain what do you
Yeah,
understand by the bulk
surface
micromachining and
bulk
surface
means
micro?
in the bulk in the bulk itself. If you want to obtain any structure, means then that is called bulk. In the silicon substrate, the whole substrate surface micromachining means it's additive process. On the surface, we are depositing. If we are depositing, means that is called additive process.
Okay, so it is
It's
surface micromachining, and
uh,
in the bulk portion, it is
uh,
bulk micromachining. Like here, it is the surface
yeah.
micromachining, and
Then
here it
off
is the
bulk.
bulk.
Yeah, both A and B.
Can you please explain about the fabrication process, how we can like fabricate this type of bulk micromachining structure? Can you please a little bit explain about the process?
So first we have to create a mask, ma'am. So take a substrate.
Okay.
Then
Uh-huh.
above that insulating layer should be deposited. Then we should create a mask that like pitta, that hollow like structure in the bulk.
How we can fabricate this hollow type of structure?
Then according to that we should create a mask. No? Then after that lithography process is completed, then we will get that kind of structure.
So we can use the photolithography process. So can
Mm.
you explain why, like which type of mask here we can use? Like
It
where,
should be
what is the
NPR.
need of the mask? Like
NPR
if is there
negative
any
photo.
use of the photoresist?
Yeah, positive photoresist. Then only that particular pattern will be transferred into mask that the substrate, silicon substrate.
Here, can you use the negative photoresist?
NPR, yeah, NPR. I think PPR now. Positive photoresist.
So we can't use the negative photoresist.
Yeah, that is also used, but uh, if you using NPR means then that hollow portion will be should be in the on the top reverse direction. I think so.
How the hollow portion can be fabricated?
Yes, ma'am. According to the mask, ma'am, we should create the mask depends based on the dimension. Then after lithography process, then
See,
that is
where
transferred
is
to
the
a
structure? Okay, here is the structure. Okay, present
yeah.
the wafer structure. Now
Yeah.
mask is here. If
Yeah.
it is
Yes, ma'am.
projection lithography, the projection or proximity like here, and
Uh,
here the UV
EV rays.
rays, yes, coming.
Yeah. Yeah.
So
Uh,
this is the mask pattern, and here is the positive or negative photoresist is there. Now
yes, ma'am.
you tell me how
Uh,
the hollow structure can be fabricated. So
I
by this
think,
question, now
ma'am,
you
from
can
the
also,
ma'am, this should be, it's like a diaphragm, ma'am. And the
yes,
pressure sensor
yes,
we are
there is a
creating
diaphragm
now.
like structure. So
Uh,
how you will fabricate this diaphragm like
yeah,
structure? My question it is.
from the top, bottom, I think so. From the from the bottom, we can etch this kind of structure.
Okay, so from the
Uh,
bottom side, we
yeah,
will like this type of a structure
yeah,
we
that's a
will.
diaphragm structure we
Okay,
will get.
so
And then
do,
after that, in the surface micro machining, we should deposit. We should get the deposit the remaining structure.
have you heard of the word the etching process?
Yeah, etching a little bit. I know.
Yes.
Mm,
So by
mm,
using the etching process, they can fabricate the hollow type of structure. So
mm.
some portion of the silicon wafer, here it is the silicon wafer. Okay.
Yeah, yes, ma'am.
So when they like they will use some photoresist or something, so
Mm,
it will covered here
yeah.
or the silicon
Then,
here is the silicon
yeah,
dioxide is
SiO2
present.
on
So
both
silicon
sides. Both
dioxide
sides we
and
should
then
deposit.
yes, and then
Uh,
it is the photoresist is there. So it will act as a mask.
yeah.
So if after that you will etch it like some etchant solution you use, so it
Uh,
will etch that portion. Okay.
uh, uh,
So which type of etch solution is used to create this type of a structure? Like silicon etching. Which
uh,
type of solution they have used? This
KOH.
discussion.
KOH.
Yes, KOA solution and another one.
Another one, KOH etching. Hydrogen H2.
No, it
I
is
forgot, ma'am.
TIMA. It is
Ah,
TIMA process.
yeah, yeah, TMO process. Yeah, correct.
So which one is more favorable?
I think
The
KOH.
YQA?
TMA means if you want to etch the rectangle type structure, na, then we should use TMA. Or
No, no.
KOH means it make
This
angle 52 point something like angle.
no. See,
Uh,
KOH and TIMA both are weight etching process. So in
uh,
weight etching process, it is if it is an anisotropic weight etching process, in that case, this type of a structure is present. So the
yes.
angle here is 54 point.
Uh,
Which
Angle
one?
is
The
50.
seven or six,
Yeah,
right?
that is KOH 54.6.
Yes,
6.
degree. It
Uh,
is it both can that angle both can happen for both cases. Okay,
okay.
but TMA it is required the higher temperature. Sorry, KOH it is required the higher temperature near about 80 degrees centigrade. But in
Uh,
TMA it can happen at room temperature. Room
oh,
temperature means 25 degrees centigrade. So now tell me, and also this TMA process is smooth. Okay, so
uh,
smoothly it can etch. Now you
yeah.
can tell me the which one is the favorable.
KOH, ma'am.
No, it is not KOH. It is require
For this
in
kind of
KOH it
structure,
require it require higher temperature also it is
yeah,
rough
yeah, 80
surface.
degree.
So
Yeah.
we can go through the which is more favorable in room temperature. We can go fabricate this and also it is smooth surface it can prepare. So TIMA process they have used. We can use both process but more favorable is TIMA. Okay.
Okay, ma'am.
Okay. So the right option is both A and B.
Okay.
So next move towards the question number 8. In the low temperature region of CVD, rate of reaction, first option is does not vary significantly with temperature. The second option is it very sensitive to temperature, and the third option is it very is very sensitive to the molecule weight of precursor, and the fourth option is that at the surface of the substrate does not depends on the crystal orientation.
Rate of reaction is very sensitive to temperature, ma'am. B.
Option B. Yes.
Uh,
Can you little bit explain?
because it's a CVD, no, ma'am. So that's
Hmm.
why it depends on chemical. It's very sensitive to temperature.
Yes, it's very
Because
sensitive to
yeah,
temperature. And
yeah.
what happened in CVD process? Do you have any idea of the atmospheric process, CVD process?
CVD
How it's look like?
chemical vapor means we have the target material, ma'am. We have the target material. So
It is
based on the
not.
chemical reaction, that particular material will be deposited on the surface.
Okay, so see, this is a structure where we can grow from the atmospheric pressure CVD. This is the third zone system. Okay, the first zone, this is the second zone, and this is the third zone. How we
Okay.
deposited at using the atmospheric pressure CVD system. So here is the inlet pipe is there. The gas in the argon gas is going here,
Yeah.
and this is the outlet. So here the exhaust gas, like after the deposition, the outlet is there, so the gas can go through here. And here we use the some precursor. Okay,
Yeah, yeah, yes, ma'am.
like
Correct.
if we want to grow some MOs2, so
Mm.
MO3 like first zone we take the
Ah,
sulfur precursor. It is in powder form, and the
ah,
second here we use the MOO3 powder. So this is the precursor. And now we set some temperature, the higher temperature, like it is required 850 degrees centigrade.
okay.
I'm giving a little bit example how we can grow using the atmospheric CVD system. Okay.
Yes, ma'am.
And this is the sulfur evaporation temperature, I think 200 degrees centigrade. So it is 200 degrees centigrade. And here we kept the sample, like in third zone, or in the second zone we can where this is the optimized area. Okay,
Ah,
so when we heat at this temperature, so this precursor start to evaporate. Okay, so
okay.
it is start to evaporate, it is in powder form. So here the argon here is the carrier gas. Okay,
Ah,
so argon gas is flowing here at something SCCM like 60 or 80 SCCM. So
okay.
it is flowing from here. So this
Ah,
precursor and this precursor, after the evaporation, it's react. Okay.
ah, yes, ma'am.
And then it is deposited on this sample. There is a
Ah,
sample here, it is
third,
deposited.
third
And
one,
the
third zone. Ah,
yes, in the third zone, and also we can use the sample if it is deposited on the second zone, we can keep the sample in the second zone. Okay. So this is the basic structure, how in APCVD system, how the like thin film is deposited. Okay, and
okay.
here is the exhaust. So this is all about the temperature. We are giving the temperature. It's near about the evaporation temperature of that material, and somehow the low pressure system we can use the gas phase precursor, like the H2S gases we can use in that case. Okay, okay.
Yes, ma'am.
So the CVD system, the rate of reaction is very sensitive towards the to the temperature.
Okay.
So this is the question number 9. Sensitivity of a VOC sensor depends on first is the temperature, second is the cross section area of the sensing region, second is the sensing material, and fourth option is all of this. So what is the right answer?
All of this, ma'am. Temperature,
Can you please
cross-sectional
little
area
bit
of sensing
explain?
region, because all the factors will be affecting the VOC sensor, I think so.
In the lecture also
Temperature,
they have discussed that when they are using the higher temperature in that time, what type of changes they are getting in VOC sensor.
I will go through it and check it, ma'am, because
So when they have
all
used
this.
the higher temperature, now the response also increase. If you go through the lecture, you can see it is clearly see there is a graph that they have shown. Some this
Okay.
type of a structure is there. When they are used the higher temperature, So the response is also increased. So
Okay.
it depends on the temperature. Second is the cross section area of the sensing region. Can you
Mm.
little bit explain about the cross section area, how the VOC sensor depends on it? If the cross section area is lesser, like the small area, in that case, what happen?
The temperature is reducing.
If it is a small area, in that case, the surface to volume ratio also changes, now.
Ah, yes, ma'am.
So what happen in that case? If the surface to volume ratio is increased, the more surface area, so more number of like VOC can react with this material. So it will, so we can get the more changes in the output result, right?
Yes,
More
ma'am.
surface area, so more VOC can react with this material. So it's
Okay, ma'am.
also depends on the cross section area of the sensing region.
Okay.
So this also right, this is also and the sensing material. So
Mm.
it depends on the sensing material. Like if some sensing material, can you give me some like example of the sensing material they have used in the lecture video? Which material they have used?
Ma'am, after 10th question, I will finish, ma'am. First, I go through the lecture video, then I come back. Otherwise,
Okay, no
because
worry. No worry,
because
no, we
well,
can discuss here.
yeah, I think
Okay,
what I'm thinking,
so
no, yeah, tell me, ma'am.
the sensing material like JDNO they have used
Is it
somewhere.
an okay, ma'am.
Like the metal oxide, some metal oxide they have used. So in some cases also, like here we can use the MOs to like ZNO MOs to like the semiconducting behavior, the metal oxides they have used. So
Okay,
sensing material also, the VOC sensor is also depends on the sensing material. Some
okay,
material is selective, like selectivity purpose, like some
selective.
material is selective towards this acetone, some material is selective towards the IPA, this type of, okay.
Okay,
So the right option is the all of the
all
above.
of
And this is the example, like sensing material, the metal oxide and some TMDC material they have used. And there is so many materials are there they have used for the VOC sensor.
POC sensors.
This is the question number 10. Volatile organic compounds are formed to their respective liquid easily because of dash. First is the low diffusivity at room temperature. Second option is the low vapor pressure at room temperature. The third option is the high vapor pressure at room temperature. And the fourth option is the high sublimation temperature. So which one is the right answer?
A low diffusivity at room temperature.
Volatile organic compounds are formed from their respective liquid easily because of which one?
First one, ma'am.
Low diffusivity at room temperature. No, this is not the right answer.
It's,
Take your time, then
high
try to put
vapor,
the answer.
high vapor pressure at room temperature. C.
Yes, option C is the right answer. So this is the question number 11. What technique is discussed for the reducing power consumption in MEMS-based VOC sensor? First is the increasing the thickness of the substrate. Second option is the decreasing the thickness of the diaphragm. Third option is the using the bulk micromachining alone. And fourth option is the using the bulk plus surface micromachining.
Consumption in space reduces also. Decreasing the thickness of the diaphragm.
Okay, can you little bit explain?
No, if the area is less, then power consumption is also less.
Okay. So if the thickness is larger,
Mm.
so when we heating na, so
Yes,
it's
ma'am.
more required more power to heat that portion. Okay.
Yes, ma'am.
So instead of this, if there is a like a thinner layer, so it require less power to heat this area. Okay.
Yes, ma'am.
So the
Yes, ma'am.
right option is the option B, right?
Yes, ma'am.
So question number 12 is which material is used as a sensing layer of VOC sensor? Silicon oxide, zinc oxide, aluminium or nickel?
Silicon dioxide. Sorry. Which material is used as a sensing layer? Zinc oxide. No?
Yes,
Is it
zinc
a no?
oxide.
Yeah.
Yes, the zinc oxide is the right option. Can you please tell me where the aluminium is used, where nickel
Contact.
used, and where
Contact.
the sulfur dioxide, silicon dioxide is used?
The aluminum is used for contact purpose. No?
Okay, and why nickel used?
Nickel. Actually, aluminum is more sensitive than nickel. No? Nickel that uh, the square like what is it? The channel like structure we are using nickel.
The nickel is used to deposit the heater, micro heater. Like this type of a structure is there. There is a micro heater is present to increase the temperature of the right. So
Yes, ma'am.
the micro heater is deposited by using this nickel, and by using the aluminium,
Mm.
it is the contact pad, right, where
Okay.
we can
Yeah.
take the output like source and drain.
Yeah. Yes, ma'am.
Okay, and where the silicon dioxide used?
Silicon dioxide is used as insulator,
Okay, somewhere
insulating layer,
insulator and
insulating layer, a sacrificial layer also we can use it.
okay in sacrificial use. And what about the dielectric layer, like the gate dielectric?
Yeah, that is also useful.
Yes. So silicon dioxide can use as a dielectric, some insulating layer. Yeah, it can use as a mask also, right?
Ah,
So
yes, ma'am.
the protect some portions, silicon dioxide is used.
Yes, ma'am.
Okay. So and also some passivation layer we can use.
Yes, ma'am.
So this is the question number 13. What is the primary function of the zinc oxide layer in the sensor fabrication process? First is to act as a conductor. Second, to serve as a sacrificial layer. Third option, to provide the mechanical strain. The fourth option is to act as an insulating layer.
Fabrication process. Um, to provide a mechanical strength,
Hmm?
C, ma'am,
No,
because
please go through the.
either A or C, ma'am, because sacrificial insulating layer not required, but to act as a conductor or A or C.
No.
Because Z was a sensing
Take your
material,
time. The in the lecture
right?
video they have they have shown. See the structure. This is the structure. So what they have done, they have deposited the zinc oxide here. Okay, and
Yes, ma'am.
then they have also the mechanical polishing, the surface mechanical polishing they have done. So here is the structure, and only that portion the zinc oxide is present. In the lecture video, you can see this is
Yes.
the ZNO, zinc oxide. Okay, so then they have deposited some oxide layer here, and also they have done some this type of surface micro machining, and after that they have removed that portion by etching. The
Yes, ma'am.
ZNO etching, they have removed that portion. So this type of a structure is there, like the bulk micromachining and also the surface micromachining. So after the work, the fabrication, they have removed the ZNO. Now tell me what is the right answer.
Sacrificial layer, ma'am.
Yes, its access is
To serve
sacrificial
as a
layer.
sacrificial layer.
Yes. So which one is the sacrificial layer which is used
Uh,
and also after the work or after the fabrication it is removed. This is
yeah,
called a sacrificial
completely
layer.
removed. Yes, ma'am.
Yes. So here Jadeno is used as a sacrificial layer.
Sacrificial layer.
Yes. The question number 14. What is the role of the interdigited electrode in VUC sensor? First, to provide heat to the sensing layer. Second, to act as a sensing element. Third, to measure the change in the capacitance. And fourth, to provide the structural support.
To measure the C, ma'am. To measure the change in capacitance.
Mm,
Interdigited electrodes.
okay,
So option C, ma'am. Because to measure the change in capacitance.
okay. So the right option is the option C.
Yes, ma'am.
This is the question number 15. What is used to planarize the zinc oxide layer? First option is the chemical mechanical polishing. Second is etching in KOH. Third is the dry etching. And the fourth option is the annealing. What is used to planarize the zinc oxide layer?
Uh, chemical mechanical polishing, ma'am.
Yes, the right option is chemical mechanical
Chemical mechanical
polishing.
polishing.
And where they have used the planarized process, I have already discussed in the last
Yeah, VOC, ma'am.
question.
The VOC sensor.
Yes, in VOC sensor and also where the ZNO is deposited now. So
Yeah, yes,
here
ma'am.
only this portion and this portion they have removed now. So
Yeah.
they have used the chemical mechanical polishing. So
Uh,
only the middle area there is the ZNO is present, and after the proper surface micromachining, bulk micromachining, they have removed that
remove
portion, the
that portion.
ZNO. Okay.
Okay. Okay.
So we are moving towards the question number 16. Why is the backside of the wafer protected during the BHF etching? First option is to prevent the contamination. Second, to avoid the etching silicon dioxide on the backside. Third option, to ensure the uniform etching. And the fourth option is to protect the silicon layer.
To prevent contamination.
No.
Uh,
To prevent the contamination, we can use the like the clean room, right?
yes, ma'am. And so, to avoid etching silicon dioxide on the backside.
Yes, the right option is the option
B.
B, to avoid the etching silicon dioxide on the backside.
Yes, ma'am.
Because if there is the it is not like here is the structure now
Yes, ma'am.
like this, and then there is a this is the structure. So if it is not protected that this side now, there is a
Yes, ma'am.
silicon dioxide present. So
Uh,
when we dip the wafer into the
backside
BHF
etching.
solution, the oxide BHF used for
Uh,
etching the SiO2. Okay.
okay. Okay.
So if the SiO2 on the back side is not protected, like they have used the photoresist, they can use the photoresist to
Yeah.
protect that portion,
Mm.
and otherwise the when they use this portion deep into the BHF solution, this oxide also remove on the surface of the Si wafer.
Yes, ma'am.
Okay. So the right option is option B.
B.
This is the question number 17. What is the primary function of the diaphragm in the VOC sensor? So first to enhance the mechanical stability, the second is to reduce the overall sensor size, the third option is to lower the power consumption, and the fourth option is to increase the sensing surface area.
To lower the power consumption.
To lower the power
Power
consumption
consumption.
option,
C.
yes. Can you little bit explain option C?
If the area is more, then power consumption is increasing, ma'am. If the area is less, then power consumption is less. So the primary function
Yes.
of VOC is reduce the power consumption.
Okay. So right option is option C. So next the question number 18. Which of the following is a bulk micromachining technique? The first is the zinc oxide deposition. The second is the silicon dioxide etching. The third option is the KOH etching of the silicon. And the fourth option is the nickel deposition for microheater.
KOH etching of silicon.
Okay. So can you tell me what about the first option, second, and the fourth option? If we deposit the silicon oxide, sorry, zinc oxide, so it is the part of which portion, like bulk micromachining or the surface micromachining?
Is it a no in the bulk, ma'am? The VOC
Mm.
sensor we are etching that hollow actual
Like,
zinc oxide only.
is some layer is deposited, so it is deposited some surface, right?
Yeah,
So
yeah,
in
that is
that case, you can tell it the surface micromachining, right?
surface. Yeah, yes, ma'am. Zinc
And what
oxide
about the
deposition surface.
silicon dioxide etching?
That is also surface micro machining.
Yes, because the silicon wafer is like this here you can see this is the thickness of the if the this is the thickness of the SI. So
Yes, ma'am.
only some nanometer, it is micrometer is the silicon at the nanometer range the oxide is present. So
Yes,
if
ma'am.
you etch na some portion only
Mm.
nanometer, so it is on the surface of the silicon wafer. So
Yes, ma'am.
it also called the surface
Surface micro
micromachining.
machining. Mm.
But if we use the KOH
KOH
solution to etch the
because
silicon,
that
so
it makes the angle 54.6 in the
yes, yes,
bottom only. Yeah, KOH
yes.
etching of silicon.
So this is
And
the right
in
option.
the last
And
one, ma'am, nickel deposition for micro heater,
hmm,
that is also surface.
yes, because on the surface side, when we are doing the surface micro machining, then we deposit this for micro machining, we deposit the nickel, and then we
Mm.
go through the photolithography process and we pattern.
Okay.
Okay. So this is the question number 19. How is silicon dioxide removed from the contact area? So first option is the by dry etching process. The second option is the by wet etching process in HF. The third option is by mechanical polishing. And the fourth option is by thermal oxidation. So what
Thermal
is the right answer?
oxidation. Thermal oxidation.
Can you please
So,
explain about the thermal oxidation process?
it's-
At first, tell me about the thermal oxidation. What is the thermal oxidation process?
in the furnace, thermal oxidation. If you want to deposit any material means, then we keep we put
No,
that
not
wafer in
any
the
material.
furnace
Oxidation is used. So oxide layer will deposit.
side. Ah, yeah.
Okay, thermal, it is means some temperature is there. In the presence of some temperature, some oxide, some silicon oxide layer is deposited.
Deposit. Oh,
Now
thin
tell
film.
me the different thermal oxidation process.
Thermal chemical vapor deposition.
No, no, no.
Thermal, sorry.
This is not the thermal. This is the like deposition process, like material
Yeah,
deposition,
yeah,
like
yeah. This is
ZNO
oxidation.
or MOS2. Because here the oxide is deposited, so thermal oxidation is two types. Have you heard about the dry oxidation and the wet
Dry and
oxidation
wet
process?
oxidation. Yes, ma'am. Using
Yes.
gas, then that is called a dry.
And what
Wet
about the wet
oxidation,
oxidation
wet
process?
oxidation using chemicals more.
No
Wet. Uh, if you are
oxidation.
sending gas, then if you are sending the gas means then that is coming under the dry etching. If you want to remove any particular material like that, using that gas, we can etch the unwanted material.
See what happened in dry oxidation process.
Uh, that
Dry
argon
oxidation
gas.
process, like the oxygen precursor is like oxygen gas is used in gaseous form, and also it's react at high temperature. It's react with the silicon, and it's prepare the SiO2. And what temperature they have used?
For which one?
Like
SiO2.
the greater than the 1000-degree temperature they have used. And
Uh,
what about the wet oxidation process?
oxidation. Using
Wet
etchant.
oxidation process they have used oxygen and also the water vapor. Okay, so
Uh,
that's why it is called the wet oxidation process. The water vapor H2O they have used. Okay, and
okay.
then it's react with the silicon and it's prepared the silicon dioxide. So what is the main difference? Only the oxygen is used for dry oxidation process, or it's react with the silicon, and this is the very slow process, but the quality is good. That's why for dielectric depositing the dielectric layer, the dry oxidation process you and the wet oxidation process, the water vapor is used
Water
and
vapor.
also oxygen, and it's react with the silicon and it prepared the SiO2,
Yes,
and it is the quick process like little time like 10 minutes 15 minutes you can deposit more, the thickness is more, but the quality is not that much good because the hydrogen gas also produces here, so it
Okay.
decreases the quality. Okay,
Okay.
so if you need the good quality then you can go through the dry oxidation
Dry
process,
oxidation. Mm.
and if you need the like more thickness or passivation layer or insulating layer, so in that case you can use the wet oxidation
Wet
process. Okay.
oxidation. Okay.
So now tell me the right answer. So how the silicon dioxide removed from the contact area? So thermal oxidation is not the process of removing the silicon dioxide. It is the deposition process of the silicon dioxide. Okay.
Mm. Yes, ma'am.
So this is not the right answer. One by one, you go through the option.
So, the first one, dry etching.
Dry etching process. See, dry etching process is not the right answer. Dry etching process where they have used like this type of a structure they want. Like this is the particular like rectangular shape they where they want the rectangular shape. In that case they have used. So not basically etch the remove from the contact area. They don't use the silicon
Then
the dry etching process.
contact area. Contact area, no, then hydrofluoric acid, ma'am. Isotropic
Yes,
etching. Wet
yes,
etching in
yes.
HF. Wet
They
etching in HF.
use the wet etching in HF solution. So oxide layer, like oxide layer
Yes, ma'am.
by BHF solution, they can remove. Okay, so the right option is option B.
Okay, ma'am.
So this is the question number 20. Which gas is typically used for the oxidation process in MEMS fabrication? First is the nitrogen, second oxygen, third argon, and fourth is the hydrogen.
Oxidation process. Oxidation. Oxygen.
Yes, the oxygen is the right option. This is the question number 21. How does the surface to volume ratio of nanostructure affect the sensor sensitivity? It decreases the sensitivity, it has no effect on sensitivity, it increases the sensitivity, and the fourth option is it only affects the selectivity.
It affects the. It only affects the selectivity, Amma.
Just it's only affect the selectivity. What do you understand by the selectivity word? Like if there is a five gases is present, okay,
Okay.
like the acetone is present, IPA present, hydrogen peroxide is present. So now I want that my device will detect only, matlab, it's gives the better response for hydrogen peroxide, the H2O2.
Uh,
In that case, we will call it like it is giving the highest response for selectivity, and acetone, and for the IPA it is giving it's little bit like this is the structure. This is the like 70% or 80% response we are getting for hydrogen peroxide, and for acetone it is giving 5 or 10, and for IPA it is giving 2 or 3. In that case, this device is called selective toward the hydrogen peroxide. Okay.
hydrogen peroxide. Yes, ma'am.
So this is about the selectivity. It means
Selective.
particularly one selective gas or selective VOC or molecule it is detecting rather than the other molecules. Okay.
Okay.
Now coming to the point sensitivity, like it is sensing this material. Um, in that case, we can give the sensitivity
Yes,
like
ma'am.
the delta I or delta R by Rg,
Mm.
like how much the resistance, like if it is the chemi resistance, then how much the resistance is changed is when it is compared to the base device, the when no gas is present. In that time, when you are interacting with the gas, different gases, in that
And
case how much
then
the resistance
sensitivity.
change. Okay, in
Uh,
that case it is called the sensitivity.
yes, ma'am.
So now the question is, how does the surface to volume ratio of nanostructure affect the sensor sensitivity? And now coming to the point, what is the surface to volume ratio? Here you can tell me, like this type of a structure is present. This is the volume, okay? The in the inner
Yes,
part is the
ma'am.
volume, and this is the surface, like that portion, that, and that's this portion and this. Now here is the surface to volume ratio. Like the surface, it is S, so surface by volume, this ratio will greater, or I if I take the smaller size like this type of structure, in that case the surface by volume ratio will greater. Like which one is the bigger surface to volume ratio? Like here you can see only this portion, this and this. This is the surface area, and the volume is the total. Here is the volume is same, but see the surface area. Each side the biomolecule and the VOC can interact, like each of the side. So the surface area here increased, right?
Yes, ma'am.
Yes. So here the surface to volume ratio is increased. So if the surface, it means the surface area is greater compared to the volume. Okay. So if the
Yes, ma'am.
surface area is greater, in that case, more number of molecule or more number of VOC or gases can interact with that material. So maximum changes you can get. Okay.
Yes, ma'am.
So now tell me the right answer. Take your time, but give me the right answer. More surface area, it's when more molecule absorb on the surface.
Yes, ma'am.
So it decreases the sensitivity. No,
Yeah,
right?
more area means yeah.
So this option is not the right option. First one. Then tell me about the second option. It has no
It has
effect
no
on the
effect on
sensitivity.
sensitivity. Uh,
Why?
that is, yes, ma'am. It has no.
It has no effect on the sensitivity.
No,
Like
no,
the
that is wrong, ma'am.
this is wrong. Yes,
Yeah,
this
that
is
is
wrong.
wrong.
And what about the third
Increase
option?
sensitivity. The surface by volume ratio is more than sensitivity is more.
Sensitivity is also more. So
Uh,
this option is the right answer.
right
Okay.
answer. Yes, ma'am.
And it only affects on the selectivity. No, it not only, it
Uh,
also affects on the sensitivity.
sensitivity.
So the right option is the option C.
Yes, ma'am.
So this is the question number 22. What is the thickness of the zinc thin film used in the described experiment? 0.1 micron, 1 micron, 200 nanometer, and 500 nanometer. So what is the thickness of the zinc thin film used in the described experiment?
200 nanometer, ma'am.
No, it is 500 nanometer.
Okay.
This is the question number 23. What is the purpose of introducing the nitrogen into the chamber with the VOC? The first option is to increase the temperature. The second option is to remove the oxygen. The third option is to carry the VOC vapor into the chamber. And the fourth option is to decrease the concentration of the VOC.
To carry the VOC vapors into the chamber.
Okay. Yes, the right option is the option C. To carry the VOC into the chamber. This is the question number 24. Which of the following material is mentioned as a possible alternative for nanostructure? Sensing layer. First option is the copper oxide nanowires. Second option is the WO3. Third option is the SNO2. And the fourth option is the all of the above.
All the above.
Can you little bit explain?
I don't know, ma'am, but I'm thinking the last one.
Yes, because the copper oxide nanowire also used, it is also the metal oxide, WO3 also the metal oxide and SNO2. So this all three are the use they can used for the sensing layer. The right option is the option D. Because when there this device is interact, this material is interact with the gaseous molecule now, so in that case there the structure, the material properties changes. Do you know how the chemiresistive devices work? Like if this is the silicon wafer, is a wafer, and here is the oxide layer is present, silicon dioxide,
Yes, ma'am.
SiO2 layer is present, and here is the material is deposited, some metal oxide is there like the SNO2, and here is the contact is present like the source and drain. Okay,
Ah, yes, ma'am.
so in chemiresistive devices what happen, when the devices interact with the biomolecules or the gaseous molecules or the VOCs, it absorbs on the surface of the SNO2 and it changes its property, like electrical property. So in chemiresistive device, what happens? It changes its resistance. So this is the source and this is the drain. So by using the source drain, they measure when the biomolecule or the VOC is not present on the device, and when it is interact with the molecule. So if there is no gas is present, in that case the resistance is Rg. Sorry, R device RD. And when the gas is present, in that time they have measured the resistance. So it is the Rg for in the presence of gas, the resistance. So they calculated the sensitivity. How they calculate? Delta R. It means the
Delta R by
resistance change.
RG.
Yes,
Yes.
the Rg is the um, resistance when the gas is present, and Rd is the resistance when the gas is not present. And by the RD, sorry, this is the RD, the device resistance. Okay, the when the gas is not present. So this is the sensitivity formula. So by using this formula, they have ch- checked how much resistance is changed in the device when the gas is present. Okay,
Yes.
the input, like here the input is the gas, and the changes of the material is they are observed. The output is in the term of the resistance. So when they interact with the gaseous molecule, the resistance is changed. So this is the way the devices work. Okay.
Okay.
So this is the working phenomena of the metal oxide. Like they are here they can use the copper oxide, the WO3 also use, and the
SN.
SNO2 they can use. So the
Yes.
right option is all of the above.
Okay.
So next question is 25. So what is the purpose of the differential amplifier in the sensor's electronic module? First option is to increase the temperature of the sensor. The second option is to amplify the difference in voltage caused by the change in resistance. The third option to decrease the sensor sensitivity, and the fourth option is to regulate the flow of nitrogen. So which one is the right answer?
To amplify the difference in voltage caused by change in resistance.
Yes. The option B is the right option. So next is the question number 26. How can selectivity for a particular VOC can be improved according to the text? So first option is the by increase the concentration of nitrogen. Second, by using a group of sensor in a sensor array connected to an artificial neural network. And the third option by using the thicker zinc oxide film. And the fourth option is by only using one type of sensor. So which one is the right option?
By using a thicker zinc oxide.
No.
How can selectivity for a particular VOC be improved according to the next?
Take your time, but give me the right answer.
By increasing the concentration of nitrogen.
No. Nitrogen is a carrier gas, right?
Uh,
So there is no role in the nitrogen concentration. Selectivity for a particular VOC can be improved by using thicker. So a thin layer of oxide also give the good result. Okay, so the third option is not the right option. One by one, we can go through it. This is not the right option. By increasing the concentration of the nitrogen, it's not also the right option because nitrogen is a carrier gas. Now coming to the D, by only using one type of sensor, no. To improve the VOC, they have used the sensor array. So not one, the multiple number of the sensor they have used. And then after that, they have used is some other artificial network. Okay. So
okay.
right option is option B. They have used the multiple sensor. This is called the sensor array.
Mm.
This is the multiple sensor they have used. So it improved the sensitivity. This is the question number 27. Which process is mentioned in the text as being used for etching the silicon wafer? Wet etching, lithography, batch process, and chemical vapor deposition process. Which process is mentioned in the text as being used for etching the silicon wafer?
Silicon lithography process, ma'am.
No.
Which
In the
process is
lecture,
mentioned?
they have mentioned which process they have used. Like this type of a structure is there, this much and that, then that much they have used H, then that much they have used. In there, they have you mentioned which process they have used to age the silicon wafer. Which process mentioned in the text, like in the recorded video lecture, they have used which process to age the silicon wafer. This rectangular type of structure they have used. Like if you go through the TIMA or the
Wet,
K-based solution, the
wet etching.
anisotropic age process,
Wet
wet
etching,
process
ma'am.
they have used.
Wet
So not,
etching.
no, not wet etching. Wet etching, this type of structure coming. But in the lecture video, this rectangular structure they have mentioned. So how they have, which process they have used. Not the chemical vapor deposition because it is deposition, not etching process. Now lithography or Bosch.
Is it lithography, ma'am?
No, this is the Bosch
Then watch.
process. They have used option C. Okay. Please go through the lecture video.
Okay.
There they have mentioned the Bosch process. They have this type of rectangular shape they have prepared. Okay.
Okay.
So this is the question number 28. What is the primary reason for depositing the silicon nitride during the fabrication of the piezoresistive micro cantilever? The first option is to increase the electrical conductivity. The second option is to compensate the stress caused by the silicon dioxide. The third option is to reduce the manufacturing cost. And the fourth option is to enhance the mechanical strength of the cantilever.
To increase the electrical conductivity, ma'am.
28.
28. A.
Mhm. What is the primary reason for
Primary
depositing
reason for
silicon
depositing.
nitride? At first, tell me what is silicon nitride used as which material? Like it acts as a dielectric layer,
Yeah,
like the
dielectric layer.
oxide, like in silicon nitride Si3 and 4. This is the
Yes, ma'am.
silicon nitride Si3 and 4. Somehow the passivation layer we can use the silicon nitride.
Yes, ma'am. Passivation layer, insulating layer.
So to increase the electrical conductivity it is not the right option, right? So it's
Yes.
acts as an insulator somehow. To
Uh,
compensate the stress caused by the silicon dioxide, to reduce the manufacturing cost,
mm,
no. To enhance the mechanical strength of the cantilever,
to compensate the stress caused by the SiO2.
yes, this is the right option. To compensate the stress caused by the silicon dioxide. So now moving toward the question number 29. What are the two primary techniques for thin film deposition mentioned in the text? First is the sputtering and evaporation, lithography etching, PVD or CVD, or spin coating and CVD.
Favorite technique. For thin film deposition, CVD and PVD, ma'am.
Yes, the right option is CVD and
CVD and
PVD.
PVD.
So this is the question number 30. Which process is used to produce the high purity and high performance solid material? PVD, CVD, lithography, or electroplating?
Which process used to produce a high purity, high performance? Previous with 30. Which process used to produce a high purity and high performance? Performance.
Like the purity, when you want the pure material, deposited pure material, in that case, which process we used?
Purity team of this which
No. Take your time.
process is
We'll try to
used
give the right answer.
process is used to produce high high CVD.
Yes, the right option is the CVD. Good quality thin film we can get from the CVD process. Okay. And this is the question number 31. What is the significant disadvantage of the physical vapor deposition mentioned in the text? High cost, complex process, poor step coverage, require high temperature. So this is the last question.
Right, sir.
Disadvantage of physical device mentioned that it's high
Sir,
cost.
ஒரே நிமிஷம் சார், நான் அவங்கள பஸ் ஏறி சென்னைக்கு போங்க நான் நோட்டுக்கு. நான் அப்படியே ஸ்டாப் பண்ணிடுறேன். அது ஒரு அவங்க சொல்லிடுறேன் சார்.
Poor step coverage, ma'am.
Yes, the right option is the poor step coverage. So here we close the session because I have only 31 question.
Okay,
so in the
ma'am.
next meeting, I think next class, next Tuesday, 7 to 9 p.m. Okay.
Okay, thank you so much.
Okay.
Thank you,
Ma'am, are you a student? Are you a
Faculty.
professor?
Faculty.
Okay.
Yes,
From
ma'am.
where?
From Chidambaram Annamala University, ma'am.
Okay.
Tamil
Okay,
Nadu.
ma'am.
Yeah.
Okay.
Thank you so
Okay.
much, ma'am. Thank you.
Okay. Thank you.